In this video, we want to look at a very important equation, the Henderson-Hasselbalch equation. And using this equation, we are going to calculate the pH of an acid, usually a weak acid and a weak base. We are also going to use the solution to look at buffer solutions and the calculations that are involved. So let's look at how we can derive this equation. So first of all, let's consider the following equation. So in this equation, we have the acid represented as HA. We have water to give us the hydronium ion and a conjugate base. Now, this equation can have an equilibrium constant, which is Ka. So the equation can have a Ka. So we'll say Ka of this equation, Ka is equal to the concentration of the products divided by the concentration of the reactant. In this case, the reactant is HA because water is not included in the equilibrium expression. So that is our Ka. Now, if you play around with this equation, you will find that if we make the hydronium ion subject of the formula, so we'll have H3O plus. This one will actually be equal to Ka, then Ha divided by the total of that divided by A minus. That's what is going to happen. Now, if you take the negative logarithms of both sides, then you say minus log of H3O plus will be equal to minus log of this whole expression we see here, Ka Ha divided by A minus. That's what we are going to have. But then we know that this part minus log H3O plus is equal to pH. So we can say that pH is given by laws of logarithms. This one will be equal to minus log Ka minus log Ha divided by the concentration of A minus. Now, if we can go on, minus log Ka is called pKa. It is the same as this one. Minus log concentration of H3O plus is known as pH. So minus log Ka is equal to pKa. So I'll put this one in here. It's very important. So if we go back to this equation, we'll say that pH is equal to pKa, then minus log Ha and A minus. But in this case, we don't want to work with negatives. So what we do is we flip this. So this one goes up and this one goes down. When you do that, when you flip this here, we have a positive. So we are going to say pH is equal to pKa plus log A minus divided by log Ha. So take note that the plus here has come because we have flipped these two inside the logarithm. So A minus stands for a weak base, while Ha stands for a weak acid. So in general, this equation can be given as pH is equal to pKa plus log this weak base, the concentration of a weak base, divided by the concentration of a weak acid. So this full equation here we call it Henderson-Hasselbalch equation. So let's take note of this equation. That's the name we give to that final equation. So just put this equation in memory because we'll use it later, as you will see in our examples. So let's look at an example that we can use to solve a problem based on this equation. So using Henderson-Hasselbalch equation, calculate pH of a buffer solution that is 0.050 molar in benzoic acid. So this is our benzoic acid, and 0.15 molar sodium benzoate. Now this is our base. So this is our acid, this is our base. So the question is, what is the assumption of using HH equation? So assumption of using H equation is that X is small. So remember, we are using this equation based on the assumption that X is very small and therefore does not matter. It can be ignored in special cases. We will see what it means. So to solve this equation, we just go straight to our HH equation, which says that pH, let me just write a good H, so our HH equation, Henderson-Hasselbalch equation, says that pH is equal to pKa plus log base divided by the concentration of acid. So we know that pKa is minus log of Ka, and our Ka in this case is 6.5 times 10 to the power negative 5 plus log. We know that our acid has a concentration of, we know that our base has a concentration of 0.150 molar. So here at the top we'll put 0.150, and at the bottom we know that our acid has a concentration of 0.050. So here down here we'll put 0.050. So based on that, our pKa is 4.187. When we add this one here, 0.477. So our pH of this buffer is 4.66. So I'll just put pH here again. But then, after finding the pH, we need to take note of our assumption. We assumed that X is small. So we need to take note of that. Is this pH true? If it is true, what is the value of X? So, if I can rewrite our pH again, we said that pH is equal to 4.66. This is based on the assumption that X is small. So in this case, our X is the concentration of hydronium ion in the solution. So X is H3O plus. That's what it means. So we go back here. We know that pH is equal to negative log the concentration of the hydronium ion, which is 4.66. Therefore, the concentration of the hydronium ion in this case is 10 to the power negative 4.66, which is 2.2 times 10 to the power negative 5 molar, and that is our X. So how do we determine if X was correct? We go back and look at the original concentration of the acid. So we say the original concentration of the acid is 0.050 molar. So we use 5% rule, which means here 2.2 times 10 to the power negative 5 divided by 0.050 times 100%. This gives us 0.044%. Therefore, our approximation is valid. This implies really pH is actually 4.66. So this is how we calculate pH using the Henderson-Hasselbalch equation. Now, there is some important information that we need to know when dealing with pH, and that is based on the HH equation. So I'll just write that information here. So pH is equal to pKa. This happens only if HA is equal to A minus. That is, if the concentration of the acid is equal to the concentration of the base. pH is greater than pKa when the concentration of acid is less than the concentration of base. pH is less than pKa when the concentration of acid is greater than the concentration of base. So all this information is based on the HH equation. Important thing, we have to assume that X is small, and we need to make sure to test that assumption when using the HH equation for a weak acid.